Welcome! It is December 11th, 2025. A significant announcement from NASA has just shifted our understanding of the solar system's latest interstellar visitor. For weeks, the astronomical community has been buzzing with rumors, trading preprint papers, and leaked data sets. But today, the speculation ends and the hard science begins. NASA has officially confirmed that the interstellar comet, known as 3I Atlas, is behaving in a way that defies our standard expectations. We are looking at an object that is not merely falling through our solar system under the influence of the sun's gravity. It is being pushed. This is a story of invisible forces, precise measurements, and a mystery that has taken the combined power of the world's most advanced observatories to unravel. If you want to stay ahead of this developing story and ensure you don't miss our deep dives into the physics of the cosmos, make sure you are subscribed to the channel. We are tracking this object day by day, and you will want to be notified as new data comes in from the European Space Agency and NASA. Let's look closer at the data. The headline is simple, but the implications are profound. 3I Atlas is exhibiting an anomalous acceleration. When astronomers calculate the trajectory of a celestial body, be it a planet, an asteroid, or a comet, they primarily account for gravity. The Sun is the dominant conductor of this orbital orchestra, with the planets adding their own gravitational harmonies. Under normal circumstances, if you know the mass of the Sun and the position of the planets, you can predict exactly where an object should be at any given second. But 3I Atlas is not where it should be. It is arriving at its waypoints ahead of schedule. The new data released today quantifies this deviation with startling precision. We are seeing an acceleration that includes a radial component of 135 kilometers per day squared and a transverse component of 60 kilometers per day squared. To understand why this is shocking, we have to break down those vectors. The radial component refers to the motion directly along the line connecting the comet to the Sun. A positive radial acceleration means something is pushing it away from the Sun, fighting against the solar gravitational pull. The transverse component is perpendicular to that line, affecting the comet's orbital speed and direction sideways. Finding such a significant transverse push is particularly rare and intriguing because it implies a complex interaction with the comet's surface geometry. This contradicts what we previously thought about interstellar objects being inert, tumbling rocks. This object is active, and that activity is generating thrust. Now, you might be thinking, comets accelerate all the time, don't they? And you would be right. It is a phenomenon known as non-gravitational acceleration, usually caused by outgassing. As a comet heats up, ice turns to gas and shoots off the surface, acting like a thruster. But here is the crucial detail. 3I Atlas is behaving in a way that does not fit the standard models of cometary outgassing. Usually, the outgassing correlates neatly with the comet's distance from the Sun. The closer it gets, the hotter it becomes, the more it accelerates. But the velocity increase we are seeing here is persistent and structured in a way that suggests something more specific is happening on the surface. The math doesn't balance if we just plug in a standard dirty snowball model. The force is too strong in specific directions and too consistent to be random outbursts. So, what does this actually mean? It means we are dealing with a specific kind of engine. The acceleration is not just a chaotic venting of gas. It is a sustained propulsion that has altered the comet's speed by significant margins. We are talking about a change in velocity that, while small in the context of light speed, is massive in the context of orbital mechanics. A push of 135 kilometers per day, squared, accumulated over weeks and months, results in a trajectory shift of thousands of kilometers. This is why the initial projections of where 3I Atlas would be were slightly off. The universe was applying a force we hadn't fully accounted for. I want to pause here and ask you a question. When you hear about an interstellar object accelerating on its own, what is your first thought? Is it a natural process we haven't seen before, or does your mind go to more exotic explanations? Let me know in the comments below. I read through them after the show, and I'm curious to see where the community stands on this. Getting back to the physics, we have to consider the magnitude of these forces. The transverse component of 60 kilometers per day squared is the real puzzle piece. Radial acceleration is somewhat expected. The sun heats the side facing it. Gas blows off toward the sun, and the comet is pushed away. That's action-reaction 101. But a transverse force implies that the jets of gas are not pointing directly at the sun. They are angled. This suggests the comet is rotating, and as it rotates, the delay in heating, thermal lag, means the hottest part of the surface isn't directly under the sun, but slightly offset, like the hottest time of day, being 2 p.m. rather than noon. This afternoon heat causes gas to jet off at an angle, spinning the comet up or down and pushing it sideways. However, for the numbers to be this high, 135 radial and 60 transverse, the surface activity must be incredibly efficient. We are not seeing a massive cloud of dust that would usually accompany such a strong push. If this were a standard comet like Halley or Hale-Bopp, a push this strong would be accompanied by a tail visible to the naked eye, a massive shroud of water vapor and dust. But 3I Atlas is relatively faint. It is active, yes, but it is stealthy. The force is there, but the visual evidence of the propellant is subtle. This discrepancy is what kept scientists up at night until this confirmation. They had to rule out observational error. They had to rule out the gravitational tug of Jupiter or Saturn. They even had to rule out the pressure of sunlight itself, radiation pressure, which can push on fluffy, low-density objects. But the calculations are in, and those factors are negligible compared to the thrust we are observing. This acceleration implies a mass loss of roughly 1/10 of the comet's total mass over the course of a month. Just think about that. In just 30 days, this object is shedding 10% of its being to fuel this change in speed. It is a rapid, intense burn. If this rate continues, 3I Atlas is essentially evaporating before our eyes. This high burn rate relative to its size tells us that the volatile materials, the ices driving this engine, are extremely potent or exposed. It is not insulated by a thick crust of rock. It is raw, exposed, and reacting violently to the weak warmth of our star. The confirmation of this acceleration changes everything about how we observe the object for the rest of the month. We can no longer treat it as a passive rock. We have to treat it as a dynamic, evolving system. Every telescope pointing at it now has to account for this drift. If we didn't know about this 135 kilometers day² push, we would point the James Webb Space Telescope at a coordinate and find empty space. The comet would have moved on. This is a testament to the sensitivity of our modern instruments. We are detecting the breath of a comet across millions of kilometers of vacuum. If you are enjoying this deep dive into the mechanics of the cosmos and want to support science communication that doesn't shy away from the technical details, please hit that like button. It helps the algorithm know that there is an audience for real science news. As we wrap up this first look at the dynamics, we are left with a burning question. We know it is accelerating. We know the force is non-gravitational. We know the vector components. But what is the fuel? What substance could possibly generate this kind of thrust while remaining so elusive to our cameras? To answer that, we have to stop looking at the movement and start looking at the light. We need to analyze the spectrum. And when we do, we find something that shouldn't be there. Something that makes the acceleration look like the least weird thing about this visitor. We are talking about heavy metals floating in a vacuum where they should be frozen solid. But that is a story for the next chapter. As we established in our analysis of the trajectory, 3I Atlas is not just drifting, it is accelerating under the power of its own outgassing. But knowing that it is accelerating is only half the battle. To understand why it is moving the way it is, we have to understand what it is made of. We have to look under the hood of this interstellar engine. And when astronomers pointed their spectroscopes at this object, the chemical signature they received was so baffling that it initially looked like a data error. Building on the discovery of the anomalous acceleration, we now turn our eyes to the chemical composition. And this is where the story shifts from orbital mechanics to high-stakes chemistry. The data comes primarily from two heavyweights of astronomy: the Very Large Telescope, VLT, in Chile, specifically using its X-shooter and UVES instruments, and the James Webb Space Telescope, JWST, positioned at the L2 Lagrange point. These instruments don't just take pictures, they break light down into its constituent wavelengths, revealing the fingerprints of the elements present in the comet's coma. The first shock came from the VLT. At a distance of 3.88 astronomical units, AU, from the Sun, that is nearly 4 times the distance from Earth to the Sun, out in the freezing realm of the asteroid belt, the sensors detected the unmistakable signature of nickel vapor. Let's pause and consider how strange that is. Nickel is a heavy metal. On Earth, you need a blast furnace to melt it, let alone turn it into a gas. The temperature required to vaporize nickel is over 2,900 degrees Celsius. Yet, 3I Atlas is sitting in an environment where the ambient temperature is well below freezing. So, what does this actually mean? How do you get metal vapor in a deep freeze? This contradicts what we previously thought about the sublimation temperatures of heavy elements in comets. We usually expect to see water vapor, carbon monoxide, maybe some methane. We do not expect to see heavy metals until a comet is practically grazing the sun, screaming through the corona. But here it is at 388 AU. The leading theory is that the nickel isn't sublimating from a solid metal block. Instead, it is likely trapped inside complex molecules or organometallic compounds that break down under sunlight, releasing the nickel atoms even at low temperatures. But the weirdness doesn't stop there. The quantity of nickel found exceeds that of iron. In almost every standard model of solar system formation, iron is more abundant than nickel. To find a comet where nickel is the dominant metal vapor suggests that 3I Atlas was born in a stellar environment with a completely different chemical recipe than our own solar system. This connects to the observations made by the James Webb Space Telescope. While the VLT was hunting for metals, JWST was looking at the volatiles, the ices that drive the activity. And here is the crucial detail. JWST observed a carbon dioxide to water ratio of approximately 8:1. This is staggering. For most comets in our solar system, water is the primary driver. They are water-ice worlds with a bit of CO2 and dust mixed in. 3I Atlas is the inverse. It is a carbon dioxide world with a sprinkling of water. An 8:1 ratio means that for every molecule of water we detect, we are seeing 8 molecules of CO2. This composition explains the blue tint that astronomers have noted. In the visible and near ultraviolet spectrum, the comet has a rare, eerie blue hue. This is likely caused by ionized carbon monoxide and carbon dioxide fluorescing in the sunlight. It is not the dusty, yellow-white glow of a typical comet. It is the cool, electric blue of a gas-rich, dust-poor body. This lack of dust is another puzzle piece. The Hubble Space Telescope images have constrained the nucleus size to between 320 meters and 5.6 kilometers, but the dust plumes are surprisingly thin. If this thing is accelerating as fast as we know it is, it should be throwing off tons of material. But if that material is mostly transparent gas like CO2 rather than opaque dust, it explains why the comet looks so ghostly. The Meerkat radio telescope adds another layer to this chemical puzzle. It detected hydroxyl radicals in the coma. Hydroxyl, OH, is what you get when ultraviolet light breaks down a water molecule, H2O. The presence of hydroxyl confirms that water ice is sublimating, but the signal is weak compared to the roaring signal of the carbon dioxide. This tells us that while water is present, it is not the fuel for the engine. The water is likely a minor passenger, perhaps trapped in a matrix of frozen CO2. Let's try to visualize this. Imagine a mountain floating in space, but instead of rock, it is made of dry ice, frozen CO2. As the sunlight hits it, the dry ice doesn't melt into a liquid. It snaps directly into gas, sublimation. Because CO2 sublimates at much lower temperatures than water, this comet turned on way out in deep space long before a water comet would have woken up. This explains why we saw activity so early. But the high CO2 ratio also implies a specific origin. Comets formed in the outer fringes of a protoplanetary disk, far from their star, tend to be richer in highly volatile ices like CO and CO2 because it is cold enough for them to freeze. 3I Atlas likely formed in the dark frozen wastelands of another star system, far beyond its snow line. The chemical composition includes an anomalous Phe-Ni ratio, a persistently high CO2 to water ratio, and an excess of nickel vapor. These aren't just random trivia points, they are the forensic evidence of the comet's birth. They tell us that this object was ejected from a system that might have been richer in heavy elements, or perhaps it formed in a region where unique organometallic chemistry was common. But here is the kicker. We have a comet made mostly of dry ice, leaking heavy metal vapor and glowing blue. We know it is accelerating. The question is, how does this specific chemistry translate into the 135 km/h push we measured in the previous chapter? You can't just have gas leaking out anywhere. To get that kind of speed, you need a nozzle. You need directed thrust. And that brings us to the mechanics of sublimation. How does a frozen ball of gas turn into a rocket? And why is the acceleration so smooth despite the chaotic nature of cometary surfaces? To understand that, we have to shrink our perspective down to the molecular level and look at the invisible factory operating on the surface of 3I Atlas. Given what we now understand about the chemical makeup of 3I Atlas, a world dominated by carbon dioxide and carbon monoxide rather than water, we can finally address the mechanics of its movement. We know it is accelerating, and we know what the fuel is. Now, we need to understand the engine. How exactly does invisible gas push a mountain-sized object through the vacuum of space with such precision? This connects to a concept in astrophysics known as the rocket effect. It is a simple application of Newton's third law. For every action, there is an equal and opposite reaction. When a molecule of gas sublimates from the surface of a comet, it shoots outward. The momentum of that gas escaping pushes the nucleus in the opposite direction. If a comet were a perfect sphere and sublimated evenly from all sides, these forces would cancel each other out, and the comet wouldn't accelerate. It would just shrink. But 3I Atlas is not a perfect sphere, and it is certainly not sublimating evenly. The scientific implications include testing the limits of cometary physics using perihelion data, with non-gravitational forces arising from momentum transfer by sublimating gases. These depend on the composition of volatile materials, the distribution of surface activity, and the rotation state. And here is the crucial detail that makes 3I Atlas unique. The active surface coverage is estimated to be below 1%. Let's look closer at the data. Thermophysical and Monte Carlo modeling supports asymmetric sublimation of surface volatiles, such as CO and CO2, as an explanation for both the magnitude and direction of the acceleration. This means that 99% of the comet's surface is likely dormant, a dark, frozen crust that does nothing. But that remaining 1% is hyperactive. Imagine a dark, silent city where only one factory is running, but it is running at full capacity. Because the activity is concentrated in small, specific regions, likely vents or fissures in the crust, the gas creates a focused jet rather than a diffuse cloud. This is why the acceleration is so strong, 135 km/h radial, despite the object appearing relatively faint. It is a sniper shot of gas, not a shotgun blast. This internal factory model solves the paradox of the high acceleration and low dust visibility. If the entire surface were sublimating, we would see a massive coma. But with only localized jets, the comet can generate significant thrust without shedding a massive amount of visible dust. The gas being expelled, primarily CO and CO2, is transparent in visible light. It is invisible to the human eye and to many standard telescope filters. We are seeing the ghost of a plume, detected only by its chemical signature and the push it gives the comet. So, what does this actually mean for the comet's structure? It suggests that 3I Atlas is not a loose pile of rubble, but likely has a more cohesive structure that allows pressure to build up. If it were just a fluff ball, the pressure of the gas might blow it apart. Instead, the gas is channeled. The modeling suggests that the sublimation is happening just beneath the surface, in a subsurface layer. Sunlight penetrates the dark crust, heats the volatile ices underneath, and the gas builds up pressure until it bursts out through cracks. This mechanism, often called jetting, acts like a thruster nozzle, increasing the efficiency of the momentum transfer. This brings us back to the transverse acceleration of 60 km to 2. As we mentioned in the first chapter, this sideways push is due to the comet's rotation. But now we can add the chemical layer to that picture. Because CO and CO2 sublimate at such low temperatures, they don't need high noon sunlight to activate. They can start hissing gas in the early morning of the comet's day and continue late into the afternoon. This broad window of activity, combined with the comet's rotation, creates a complex torque that not only pushes the comet sideways, but also spins it up. The Meerkat radio telescope's detection of hydroxyl radicals gives us a clue about the exhaust of this engine. The presence of hydroxyl indicates that while water is sublimating, it is likely being dragged along by the more aggressive flow of CO2. The water ice is the passive passenger, the CO2 is the driver. This hierarchy of volatiles is critical. If this were a water-driven comet, the acceleration would drop off sharply as it moved away from the Sun. But because it is a CO2-driven engine, the acceleration remains potent even at distances where water would be frozen solid. This engine has stamina. We are essentially watching a natural physics experiment. We are testing the limits of cometary physics using perihelion data. By observing how the acceleration changes as the comet gets closer to the Sun, we can map the distribution of these vents. If the acceleration spikes suddenly, a new vent has opened. If it drops, a vent has been exhausted. We are reverse engineering the surface map of an object we cannot even resolve as more than a point of light. But this engine comes with a cost. The acceleration implies a mass loss of roughly 1/10 over the course of a month due to ice sublimation. This is a suicidal burn rate. The comet is spending its substance to buy speed. This rapid depletion raises a fascinating question about its history. If it is burning fuel this fast, it cannot have been active for very long. It must have been in a deep, cryopreserved sleep for most of its existence. This connects to the object's journey. We have looked at the speed, the chemistry, and the mechanics. Now we need to look at the timeline. Where did this object come from? How long has it been traveling through the void to get here? And if it is losing mass this quickly, will there be anything left of it by the time it leaves our solar system? To answer that, we have to rewind the clock, not by years, but by billions of years. Building on the mechanics of the invisible engine we discussed in the previous chapter, we are faced with a stark reality. 3I Atlas is burning the candle at both ends. It is accelerating, but it is dying. This rapid mass loss, roughly 1/10 of its mass in a single month, tells us that this level of activity is a recent phenomenon. It hasn't been fizzing like this for millions of years, or it would have vanished long ago. This implies that for the vast majority of its existence, 3I Atlas was a silent, frozen tomb. We are looking at a visitor from deep time. The trajectory shows a speed of 130,000 miles per hour after billions of years in interstellar space. Let that number sink in. 130,000 miles per hour. At that speed, you could travel from Earth to the Moon in under 2 hours. This velocity is the hallmark of an interstellar object. It is moving too fast to be bound by the Sun's gravity. It is just passing through. But the fact that it has traveled for billions of years implies it has crossed vast stretches of the galaxy, likely ejected from its home system during the chaotic era of planet formation. This object is a time capsule because it has been in the deep freeze of interstellar space near absolute zero. Its chemical structure has been preserved perfectly. The frozen history, locked inside its ice, is a sample of the nebula that formed its parent star. When we analyze that 8:1 CO2 to water ratio, we aren't just looking at gas. We are looking at the conditions of a star system that might have existed before Earth was even born. Let's look closer at the physical profile we have constructed. The rotation period is 16.16 hours. This is a relatively standard day for a comet, but it is a critical number for our models. A 16-hour day allows for the thermal lag we discussed earlier, the delay between high noon and peak heat, to generate that transverse thrust. If it spun too fast, the heat would be distributed too evenly. If it spun too slow, the cold side would get too cold. 16 hours is the Goldilocks zone for generating the specific torque we are observing. However, the dust loss rates are where things get messy. We are measuring rates of 0.3 to 4.2 kilograms per second. That is higher than expected for an object of this size. Remember, the nucleus is constrained between 320 meters and 5.6 kilometers. A loss of 4 kilograms every second adds up. It means the comet is shedding its skin. This dust is not just waste, it is data. Each grain of dust carries the mineralogical history of the comet. The fact that the rate is higher than expected suggests that the surface is more fragile or fluffy than a typical solar system comet. It might be that the cosmic rays it was exposed to during its interstellar voyage altered the structure of its crust, making it easier to crumble once it heated up. This contradicts what we previously thought about interstellar objects being hardened survivors. We assumed that only the toughest rocks survive the ejection and the journey. But 3I Atlas suggests that even fragile, volatile, rich bodies can survive the trip, provided they stay far away from stars. It is only now, as it plunges into the warmth of our solar system, that it is beginning to fall apart. So, what does this actually mean for the panspermia theory? While we must be careful not to speculate without evidence, the presence of complex chemistry, organic precursors, implied by the carbon-rich composition, and the mechanism of interstellar transport makes 3I Atlas a case study in how material moves between stars. It is a panspermia engine in the mechanical sense, a vehicle capable of transporting volatile chemicals and potential building blocks of life across the galaxy. The fact that it is off-gassing so violently now shows how it delivers that payload, by sublimation and dust ejection as it passes a star. The acceleration implies a mass loss of roughly 1/10 over the course of a month due to ice sublimation, which could manifest as a gas plume. This plume is the delivery mechanism. If Earth were to pass through the tail of such an object, which we are not in this case, that material would rain down into our atmosphere. 3I Atlas is demonstrating the mechanism of galactic cross-pollination right before our eyes. But this visitor is not staying. Its hyperbolic trajectory guarantees that it will leave the solar system, never to return. We have a limited window to learn its secrets. It has traveled for eons to spend just a few months in our view. The urgency of this mission cannot be overstated. We are trying to read a book that is burning itself as we turn the pages. This connects to the immediate future. The comet is rushing towards its closest approach to Earth. The data we have gathered so far, the speed, the chemistry, The rotation is just the prologue. The main event is about to begin. As 3I Atlas swings past us, we are deploying every asset we have to capture the climax of this encounter. The next few weeks will determine whether we solve the final mysteries of this object or if it takes them back into the dark. As we established in the previous chapter, 3I Atlas is a fleeting visitor, a time capsule that is rapidly unsealing itself. We are now in the final countdown to the most critical phase of this encounter. The theoretical models have been built, the chemical analysis is in, and the trajectory has been plotted. Now it is time for the close-up. The comet will make a safe approach to Earth at a distance of about 270 million kilometers on December 19th. To put that in perspective, that is roughly twice the distance between Earth and the Sun. It is not a near miss in the Hollywood sense. We are in no danger, but astronomically speaking, it is a front-row seat. This proximity allows our telescopes to resolve details that would be impossible at greater distances. We are moving from detection to characterization. Observations are ongoing using Hubble for high-resolution imaging, JWST for infrared spectroscopy, VLT for optical spectroscopy, and MeerKAT for radiosensitivity. This is a coordinated global effort. It is rare for so many major observatories to target the same object simultaneously, but the stakes justify the expense. ESA's JUICE mission, primarily designed to explore Jupiter's icy moons, is also being repurposed to monitor the gas plume. This is a unique opportunity to use a probe that is already out in deep space to get a different viewing angle than we can get from Earth. Here is the crucial detail. Astronomers expect additional data in the coming days to refine the object's dynamics. The acceleration we discussed, the 135 km/2, is not a static number. It is evolving. As the comet gets closer to the Sun, the heat increases and the sublimation should theoretically ramp up. But will it? Or will the surface crust over? Will the factory run out of fuel? Watching how the acceleration changes in real time during this approach will tell us about the internal structure of the comet. If the acceleration suddenly stops, it means the volatile ice pocket has been exhausted. If it spikes, it means a new fissure has opened. Future facilities such as the Vera Rubin Observatory will improve detection capabilities for objects like this. 3I Atlas is likely just one of many interstellar visitors that pass through our system unnoticed. The Rubin Observatory, with its massive wide-field survey, will likely find dozens, perhaps hundreds, of these objects in the coming decade. 3I Atlas is the pathfinder. It is teaching us what to look for: the blue tint, the anomalous acceleration, the carbon-rich spectrum. It is writing the field guide for the next generation of interstellar astronomy. So, what does this actually mean for the big picture? It means the solar system is not a closed box. We are part of a galactic ecosystem. Material is constantly being exchanged between stars. The water in your glass, the carbon in your cells, some fraction of that might have arrived on a vehicle very similar to 3I Atlas billions of years ago. By studying this object, we are studying the delivery mechanisms of the universe. The comet will remain observable to telescopes through September 2026. We have nearly a year of follow-up observations. As it recedes, we will watch it cool down. We will see which gases stop sublimating first. We will watch the coma fade, and eventually it will become just another faint point of light, disappearing into the dark, heading toward a destination we will never know. This brings us to the end of our deep dive. We have covered the impossible speed, the alien chemistry, the invisible engine, the frozen history, and the upcoming encounter. We have taken a ghost story and turned it into a physics lesson. But science is a living process. The numbers I gave you today, 135 kilometers, day², 8.1 ratio, might be refined by next week. That is the beauty of active research. If you found this deep dive valuable, if you appreciate the effort to break down the raw data rather than just reading the headlines, please consider liking this video. It helps us continue this work. And if you have a theory about the origin of 3I Atlas, where do you think it came from? Leave it in the comments. I'll be reading them tonight. Until next time, keep looking up.